7.5 logistic growth. So if you looked at the beginning of this unit, it said differential equations and math modeling. And the previous lesson was exponential growth and decay, and now we're into logistic growth. So this is their approach, which is kind of neat, but at the same time, I mean, it's nice, but at the end of the day, you just got to bang out a lot of math. So what is logistic growth? Logistic growth is dropping off a bunch of squirrels on an island where they can't swim to shore, and they have to have a critical mass, of course, but then they grow, and they're growing like crazy. There are no predators on the island. They're eating like crazy, or maybe there are predators on the island, but they're not aware of the squirrels at first, and they grow, and they're just coming tons of them, and then eventually they start to peak out. Why do they peak out? Because there's only so many squirrels that this small island can handle. If they eat too much, they starve. This apparently happens with deer, and that's the justification for deer hunting season. And I'm sure it has nothing to do with people wanting to, shoot a deer from a distance. But there's a maximum growth. There's a maximum possible population. Humans don't tend to follow this, although it kind of has happened. You can only fit so many people into a city before it becomes just, impossible to fit anymore. There's not enough water. There's too much sewage. They can't process it. They need a bigger plant. So yeah, it's been kind of amazing what we've been able to accomplish. Now, this, of course, is a point of inflection. And the weird thing is that this is time, and this is population, but the point of inflection happens here at the max population over 2. And when's it occur on time? We always work off the x-axis, not this time. So be aware of that. That fact right there has saved me more times than I can mention. So we'll come back to logistic growth. That's what this is about. So to do that, we have to develop a new tool. We have to break things into partial fractions. And then I'm so confused. Why does it say rational functions? No, it says partial fractions up here. Weird. Partial fractions. And then we can use logarithm, by the way, logistic logarithm. Yeah. All right. So how do we do this? All right. Hear about, I don't remember this. Yeah, it's okay. I don't expect you to. I did have a teacher who was like, why do we have to teach partial fractions? I said, because we need it in calculus. That wasn't a good enough answer for them, but I told them, then don't teach it. I can always teach it myself. We factor the bottom, 2x minus 1, 2x squared, minus x, minus 6x, minus 7x, negative, negative, positive 3. All right. And I'm so confused. Why would I write it that way? That doesn't make any sense. And we multiply everything by 2x squared minus 7x plus 3. So we're basically multiplying by 2x minus 1 times x minus 3. So when we multiply we get x minus 13 equals a times, and it's really important to write all this out. At no point in time have I ever tried to shortcut this process at all. 2x minus 1. Multiply this here, x minus 3 cancels, we're left with that. Multiply this here, they all cancel, left with that. Multiply this here, 2x minus 1 cancels, left with that. So now we cheat. We're supposed to do a system of equations. Yeah, not going to happen. Because technically I can't put 3 into this. 3 minus 3 is 0. But hey, when x equals 3, this cancels out. We get 3 minus 13, and I would never do that. I would go negative 10 equals a times 3 minus 3, 0, which we picked the 3 on purpose, plus b times 2 times 3 minus 1. Negative 10 equals 6 minus 1, 5b. b equals negative 2. Notice I picked the 3 to cancel. What do I pick here? Well, let's guess and check. Try 1/2. 2 times 1/2 is 2 minus 1. No. Try. Yeah, no, that works. What am I thinking? 2 times 1/2 is 1. 1 minus 1 is 0. Weird. X equals 1/2. And off we go again. Now life gets a little bit ugly. I need to keep things in fractions. I will in a moment. 1/2 minus 13. We're going to call this 26 over 2. 2 over 2 equals a times 1/2 minus 3 times 2 over 2 plus b times 2 times 1/2 minus 1, 0. So negative 25 over 2 equals negative 5/2 times a equals, multiplied by negative 2/5, negatives cancel, 2's cancel, a equals 5. Usually one's negative, one's positive, but I don't look into usuallys. I get what I get, and that's fine. So we could rewrite this. I can't integrate this. It's impossible as is. Hey, we got a cool technique. F of x now equals, what's a? 5 over 2x minus 1 plus negative 2, and I do write it that way instead of the minus because I'll just miss it otherwise, and I usually do. Great. At which point you're like, well, why? Why? Okay, I can now integrate. I couldn't integrate before. So we're going to practice a little bit, and then we'll finally integrate. What if the numerator has a higher power? And this is so very embarrassing to not have a dx on there. I'll have to open that up and fix it. I'm going to pause this thing, go back to my file, fix it. I just fixed it on my Word doc. Now I feel better about myself. So what if the numerator has a higher power? Oh, this is just lovely. I do have to say this is really fun because this is when I see my students scream. Yes, I can hear the screaming. X squared minus 1, 3x fourth divided by that. I got to write 0x to the third, 0x squared, 0x minus plus 1, because otherwise I'll screw it up. And I didn't leave myself a lot of space there, but that's kind of on purpose. 3x squared. Multiply, I get 3x to the fourth minus 3x, whoops, minus 3x squared. Everything becomes a negative because I'm subtracting by, and I get 3x squared plus 0x plus 1. Now we multiply by 3. 3x squared minus 3 negative plus, and I'm left with 4. All right. So I now get equals integral of 3x squared plus 3 plus 4 over x squared minus 1 dx. I can integrate, I can integrate, I can't integrate. So let's go down here and sort that out. 4 over x squared minus 1 equals a over, I do this part in my head, I apologize. Factor that, you should be able to just, boom, be done. 4 equals a, x minus 1 plus b, x plus 1, x equals 1, gone, 2 divided by 2, b equals 2. X equals negative 1, gone, a equals negative 2. So equals the integral of 3x squared plus 3 plus, and this is where people get a bother. What happened to the 4? It's gone. I rewrote this as this and this. Negative 2 over x plus 1 plus 2 over x minus 1 dx equals x to the third plus 3x minus 2 ln of x plus 1 plus 2 ln of x minus 1. Factor the 2 out, x to the third plus 3x. We'll go minus 2. All right. ln. Now, when I take the negative out, I get minus that and just that. So that's x plus 1 minus x minus 1. X plus 1, x minus 1. I've waited till the end to put it in, plus c. Yeah, that's serious math, boys and girls. That's not for the faint of heart. Alrighty. Now, oh yeah, 3 roots equals a over x plus 2 plus b over x minus 2 plus c over x minus 1. So 6x squared minus 8x minus 4 equals a times x minus 2, x minus 1 plus b times x plus 2, x minus 1 plus c times x plus 2, x minus 2. That's hard. All right. X equals 2. I did all this off to the side. I can't do that. Wow, this is hard. So 24 minus 16, 8 minus 4 is 4. 4 equals gone, gone. 2 plus 2, 4, 1. 4b, b equals 1. Wow, I'm gonna roll. X equals, I don't want to do negative 2. Better do it first then. Negative 2. 24 plus 16, 40 minus 4, 36 equals negative 2, gone, gone. Negative 2 minus 2, negative 4 times negative 3 is 12. 12a, a equals 3. X equals 1. That should be easy. 6 minus 8, negative 2 minus 4. Negative 6 equals 1 by negative 3c. 1 plus 2 is 3. Negative 3c. C equals 2. Man, that's hard work. All right. So y equals the integral 3 over x plus 2 plus 1 over x minus 2 plus 2 over x minus 1 dx equals 3 ln of x plus 2 plus ln of x minus 2 plus 2 ln of x minus 1 plus c. They're all being added, so I can just change it into multiplication. And then I can take the 3 and put it into a power. Weird. You can stop there, that's fine. But if we're gonna be cool math people, ln of x plus 2 to the third, x minus 2, x minus 1 squared plus c. No, I would never, ever, ever, ever see that on an AP test or even one of my math tests. Yeah, I might have done it on one of my math tests, but I'm not sure. So yeah, that's just practice. Back to the logistic curve. So P stands for population, like I showed you on the graph before. M stands for max population. And by the way, I will show you what I think about that logistic curve in a minute. And K is constant again, just like in exponential growth. So again, we have this going on. M, 1/2 M. I personally think the population probably jumps up, comes down, and does this little oscillating thing until it settles in here at its long term. But we can change things and introduce wolves back to Yellowstone, and things got a lot different than they were before. So let's start giving you examples, and we'll show you the horrible math, which I got really, 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 really nice about. It happens. I'll try not to let it happen again. Okay, so growth rate bears in newly established wildlife preserve, which they can't get out of apparently, or maybe it's just a forest and they don't want to leave, and everything's a little sketch here. But what are you going to do? What is the carrying capacity for bears in the wildlife preserve? 100. And again, I might, hey, you go out and you tag the bears and you count them up. And there's 105. Next year there's 97, and then there's 101. Then I don't know how fast bears reproduce and all that. What is the bear population when the population is growing fastest? $50 bears. What is the rate of change when it's growing the fastest? Well, dp/dt equals 0.008 times 50 times 100 minus 50 equals 20 bears per year. So the bears show up, there's lots to eat, they're happy as can be, they take off, they start producing like crazy, and they're right in here going at 20 bears per year. But then things just start getting a little harder to find food, so on and so on. In the late 80s, 61, had a great number. I would imagine they're like, we're going to get 75 Canadian moose, and they got like 61. They're like, man, this is really hard. We're done. We're introduced in the Upper Peninsula of Michigan. Let's hope the moose will hit the carrying capacity in 25 years. The growth rate was this. According to the model, what's the carrying capacity? Thousand moose. So what's the slope field look like? Let's put in calculator. Or Desmos, wherever you have a program, because I'm not about to draw a slope field for that. All right, solve the differential equation. This is really, really tricky, so I'll show you how it works. Remember this. Remember this. Remember partial fractions. Here it comes. So I typed it up, which is a little weird, but what are you going to do? So there's our formula. There's our initial condition. Come back to that much, 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 much later. Bring the p's over, and here we go. We got a partial fraction to break out, so we'll break it out. 1 over p, a over p, multiply by 1,000 minus p, and p, get 1, 1,000 p. If p is 1,000, a is 1 over 1,000. If p is 0, to make that 0, 1 over 1,000. So we rewrite, keep the dp. We factor out the 1 over 1,000. We do that. Then we multiply both sides by 1,000. Makes our lives a little bit easier. All right. Now we slap in our integral. We're ready to go. Piece of cake on the right, 0.3t dt plus c. The left is ln of p. Now watch it. We finally get a chain rule thing. Minus. Where'd the minus come from? Derivative is 1 over that times -1. So you have to have a minus there. All right. ln of p over 1,000 minus p, because that's easier. And then we're going to e it. And then we're going to break these apart like we always do, e to the c. We're going to use that to find our initial amount. Okay, just call it an amount. All right, and now things get really dicey. People go, whoa, what just happened? Flip the e upside down and put a negative in front. Flip this upside down. This is why I didn't do this by hand, because people would just want to cry. And I don't blame them. So let's go find that a. Plug in the original value of 0, and we get 61. So the population is 61, 61, plug in 0, e to the 0 is 1, so A is 15.393. Everybody, well, you started with 15. I thought you started with 61. Don't get hung up on that. We haven't even come close to what the formula is going to look like. Okay, so there we are. Now what do we do? This reminds me of when I used to coach. Today we're working on this, don't do that. No, today we're working on that, don't do this. We shove everything together. Oh no, wait, we're breaking it apart again. Why would we do that? Because I can rewrite this as 1. I can add it over. And then I can flip everything and multiply by 1,000. Maximum carrying capacity, 1,000. What does this mean? Doesn't matter. It's just a number there. So, hey, I want to know the population at any time. Plug in T, you got it. This, you might think, is insane. This is what a logistic looks like. If you do a logistic, wink, wink, hint, hint, on your calculator, that's what it's going to give it to you as, which seems totally insane. That's just the way it works. It's almost like somebody decided to build it that way. No, if you solve for P, this is what it works out to every time. So there it is. Everyone's going to be like that. M is your maximum population. All right. K is some weird constant, which came down from the other one. M is still your maximum population. A is some constant. Based on initial conditions. All right. So here's the population of a town. We're going to use a logistic regression to go put it in. That, edit, clear. Don't know how that happened. Well, I do know how it happened. I mishit. Clear, enter. So 0, 20, 30, 40, 50, 53. Cool. Stat, calc, logistic. Slick, huh? L1, L2. I like to store things. Alpha, calc, 1Y1. I'm just a fan. And check it out. All right. There it is. C over. C is 316,440. That's my maximum capacity. So what's it saying? What will the population, what would be the population along? Actually, let's go up here and write it in. P equals 316,440.713 over 1 plus 23.577 e to the negative 0.103 t. What will be the population in the long run? Looks like it's going to max out at 316,000-ish. Again, human beings have an incredible capacity to, do things that we probably shouldn't be doing. Now, let me just back up and say, when people freak out, because this is pretty challenging stuff, this is where you're going in a world of statistics. If that's the kind of major you want to choose, which I highly recommend. It's a very fulfilling major, although you really do get in the numbers. Now, you'd have to qualify it. Well, this is based on what growth we've seen so far. It grew really fast and slowed down. Explain Detroit to me. Detroit is losing population. All right, there's all sorts of other things that are happening. But this is just a rough idea. Maximum carrying capacity. Remember this one. This one I can't overstate. This is a question on every second or third test, it seems. this one right here. Sorry about that. All right. P times something minus P. dp dt equals, Kp something minus P. Memorize that. Memorize that. That'll save you a lot of aggravation. Know this half thing. That'll save you a lot of aggravation. The other thing to learn from the lesson is the partial fractions and how to do that. Pops up all the time. Goodness gracious. Lots of work. Good luck. Happy math.